Hello and welcome to the wolfSSL live webinar, wolfBoot Security on the STM32H5 with PQC, presented by wolfSSL Senior Software Engineer David Gorski and ST Microelectronics Product Marketing Engineer Mina Lambakis. My name is Shizuka and I'll be moderating the webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. If you'd like to stay updated with all the latest from wolfSSL and ST Microelectronics, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Also, feel free to email us at fax@wolfSSL.com if you have any additional questions. And now, I would like to turn it over to David and Mina to talk about wolfBoot security on the STM32H5 with PQC.
Thank you, Shizuka. Today we're going to talk about wolfBoot security on the STM32H5 with post-quantum cryptography. My name is David Garski and I'm a senior software engineer at wolfSSL. And today we'll present together with Mina Rumbakis, who is from ST. Quick introduction of wolfSSL and the H5, and then we'll go into the details of wolfBoot, including a live demo. So wolfSSL started in 2004 when MySQL needed a clean room implementation of SSL back then. And in 2006, we rewrote it as a C library, which then became wolfSSL. Today we have over 2,500 OEM customers, 17 resale partners, including ST, and we secure over 2.5 billion connections. This is our suite of open source libraries that we have and products. The core of this is wolfCrypt, our crypto engine. This is a FIPS 140-2, 140-3 certified library, also safety critical certified with DO 178 at the DALA level. A good portion of the wolfCrypt is. We also support asynchronous cryptography, which allows us to break apart some of the softer crypto operations, the big ones like ECC and RSA, into smaller. We also allow offloading to external crypto hardware and allow the caller to return and do other work. It's a unique feature of wolfSSL. Allows for scaling. Our TLS library is called wolfSSL. It supports the latest TLS 1.3 and DTLS 1.3. There's also a sniffer component that allows inspection of TLS 1.2, 1.3 traffic if you know one of the keys that's used. We have a key manager and a whole bunch of other stuff that has been productized to be able to inspect traffic. We also support a keylogger function that works with Wireshark, which is really nice for debugging. We have an MQTT client. It's lightweight, designed for embedded. All of these libraries are written in C with some inline assembly. Our SSH library is a client server, and it supports SCP and SFTP. We have a TPM 2.0 library. wolfBoot is our secure bootloader we're going to talk about today. wolfSentry is our embedded intrusion detection and prevention system. So imagine an embedded firewall that you could put into small embedded devices. We also have a software certifiable true random number generator called wolfEntropy. We have a PQCS11 provider that can use wolfCrypt or wolfTPM underneath. We have a software HSM that can work with silicon that supports customizable HSMs. And then we have Wolf Engine, Wolf Provider, which are OpenSSL plugins. A lot of people use that to enable FIPS within OpenSSL. We have wrappers for Java, like JSSC, JNI. We have C# wrappers, Python, JavaScript. We have a wolfSCEP product, which is a simple certificate enrollment protocol. It's a standardized protocol for provisioning devices. We have secure update examples. We have a command line utility. curl, so we offer support and maintenance for curl because the maintainer of curl, Daniel Stenberg, is an employee of ours. And then he's also developed a version, a small version we call Tiny Curl, that is available. Again, all these are open source. They're GPL. They're out there on our website for download or on GitHub directly. So ST is a very important partner of ours. We're continually expanding our support. They've been very good at keeping us apprised of new hardware that's coming and being able to help get us hardware so that we can add support for things. We have gone through a lot of work to add, actually it wasn't that hard, but we added support for the CubeMX packs, which is really neat. So our libraries, you can install them, these libraries, you can install them out of the box in the CubeMX tool, and it'll generate code with these libraries that makes it really easy to try them out. I've actually done a webinar specifically on the wolfSSL Cube pack. Yeah, now we've extended it, which is great. All right, so now I'm going to hand it over to Mina, and he's going to talk about the STM32H5.
Thanks. Hello everyone, my name is Mina Mbakis. I'm going to give you a quick introduction to the STM32 portfolio, and more specifically the STM32H5 series. Here you can see the full range of the STM32 portfolio, ranging from wireless, low cost, low power, high performance, and MPUs. Highlighted in green are the microcontrollers that support the wolfBoot package. And today we're going to focus on the STM32H5 series. Here you can see the full portfolio of the STM32H5 devices. From the low-cost H503 on the left to the most fully featured H573 on the right. And here you can see the packaging and memory density options on the H5 series, ranging from the CSP25 package on the bottom left all the way up to a 176-pin LQFP or BGA package on the right. It also spans 128K flash and 32K of RAM, up to 2 megs of flash and 640K RAM. You'll notice the color code here. The light blue is without the hardware crypto, and the dark blue is with the hardware crypto. And in yellow, we also highlight the switch mode power supply option. I'll highlight here real quickly that the wolfBoot package is supported on all of these devices. You'll notice that some come with or without the hardware crypto module. If the hardware crypto module is available, the wolfBoot package can take advantage of the additional acceleration to improve performance. Here we have the block diagram of the most fully featured device, the H563/73. You can see that it is centered around a 250 MHz Cortex-M33 core that includes the floating point unit, memory protection unit, TrustZone, and embedded trace module for added debug features. To take advantage of that high speed and performance, we have two general purpose DMA controllers, the ART accelerator to help facilitate flash read and write, and then also the Cortex and FMAC DSP accelerators. As mentioned earlier, the device contains up to 2 megs of flash and 640K of RAM. You'll also see 4 kilobytes of backup RAM available as well. In the system side, we have your usual suspects of the power supply, oscillators, and real-time clock. On the memory interface, as you can see, a parallel memory interface that can support multiple memories, along with a TFT-LCD display, an OctoSPI port, and 2 SDIO ports. On the connectivity side, there's a USB port. We can also support the USB-C power delivery spec, 6 SPI ports, 2 SAI ports, 3 I2C, and a MIPI I3C interface that can also be used as an initial I2C interface. There are 2 CAN ports, multiple UARTs, and an Ethernet port available on this device as well. Including the STM32H5 processor are up to 22 timers, including 2 advanced motor control timers and 6 16-bit low power timers. On the analog side, there are 2 12-bit ADCs, 2 12-bit DACs, and a digital time sensor, all internal to the device. And on the devices that include the crypto module, you can see that we do support quite a number of security features, including crypto accelerators, unique IDs and keys, active tamper pins, secure boot supporting an immutable and updatable root of trust. And we also support our secure firmware install, or SFI for short, that can be used during manufacturing to help prevent tampering of your firmware. To dive a little deeper into the security features of the STM32H5, you'll see on the left the blocks in yellow, which are the hardware security features available. And using those hardware security features, we can then implement the security services highlighted in blue on the right. So first you'll see the memory protections, which include one-time programmable memory, readout protections, memory protection unit, decryption, on-the-fly encryption, decryption on the external flash. We also support secure debug with active tamper. In the cryptography block, you see we have a number of accelerators to help facilitate any crypto algorithms you may be running. The AES accelerator also has a side channel attack resistance. You'll also see that we have a NIST certified crypto library to help facilitate any algorithms that you may run. Under platform authentication, we support 2 boot stages with protected level states and debug authentication. For code isolation during runtime, we have 7 isolation states, implement the Arm TrustZone technology, and have dedicated key stores. All of the hardware features on the left help us implement the turnkey security services you see in blue on the right, including our Secure Manager software package. It's allowing you to easily register to clouds and servers. We also support single or multi-tenant IP protection, pre-integrate a third-party PKA lifecycle, and also support the immutable and updatable root of trust. All of this is done on the STM32H5, which is CSIP 3 and PSA Level 3 certified. And finally, we have the hardware development tools available for the H5 series. On the left, you see the Nucleo boards for the low-cost H503 and the H533, which allows you for flexible prototyping options. And on the right is the H573 Discovery Kit, which is designed to have more connectivity, including a display and several flash options on board. And in the middle, you see the Nucleo H563 board, which again is designed for flexible prototyping. It is also the board that will be used today to showcase the wolfBoot security features. That's it from me, and on to you, David.
Thank you, Mina. Now let's dive into wolfBoot. So it's a secure bootloader. It's written in C for bare metal use. It's really doesn't care what version, what type of RTOS you use. It's agnostic. It conforms to RFC 9019, which is a firmware update architecture for IoT. This used to be an IETF draft and was later finalized. Small footprint, so typically it's 10 to 16K. In our case, we're gonna do some stuff with TrustZone. We're gonna make it a little bigger, but it can run in very small space-constrained devices. It's memory safe, which means there's no use of malloc or free. We have a very simple partitioning and header scheme, and we support multiple partitions. The headers are the sizes of the headers can vary depending on the algorithm used, and the scheme is really simple. It's just like a type and a size and a value, so a tuple. And we have a really nice HAL abstraction that we've used to be able to initialize the hardware, such as set up the CPU and the flash and GPIO, anything that's needed to be able to do, out of a boot ROM, like out of an initial reset, to be able to bring up the hardware in a way that's usable. We have portable key tools that are helpful for generating and signing the firmware, and those run across any platform. So the verification of the firmware, we support all the different type of prime ECDSA curves, P256, 384, 521. All the common RSA key sizes, 2048, 3072, and 4096, and ED 25519 and ED 448. We've also recently added post-quantum support for LMS and XMSS. We support the integrity checks, the hashing of the application image using SHA-256, SHA-384, or SHA-384. And we support encrypted updates. So the updates can be encrypted or they could be encrypted on the external partition if they're stored there. And we support AES, this typo, CTR, and ChaCha 20 poly 1305. The public key-based root of trust is what we use for authentication, and we support multiple keys. And we have support for hardware-based key stores like one-time programmable memory or a trusted platform module like a TPM. The bootloader itself handles the update between partitions, and that's power fail safe. So typically what happens is the application transfers a signed firmware image to the update partition. It calls the update API, which triggers wolfBoot to do the install on the next reboot. If the application boots up successfully and marks success, then great, it's committed. If the application does not mark success, then on the next reboot, it'll actually roll back. So we keep the last known working firmware image, and we always have the ability to roll back to it up until the point that success is called. Our bootloader also supports a self-update. That is not power fail safe, and it's not something you would want to do frequently, but we do support that. We have support for external flash memories like SPI, QuadSPI, and OctaSPI. Support for hardware-assisted dual bank flash swapping. Support for delta updates, which is basically just the differences between two updates. That can help reduce the transfer size for firmware changes. We have differential power analysis like side channel resistance, glitch attack resistance through our armored mode. These are all mitigations that we've taken into account. we have support for hardware SHA and PKA acceleration. This is ST specific, and then we have support for the ST safe and the ST33K TPM. We also have a bunch of inline assembly that we've done for ARM, like Cortex-M, that is incredibly speeds up the operations, and those are available as well. In wolfBoot, we have support for TrustZone now. So ARMv8-M adds these, what's the CSME? It's the secure, non-secure domains, but basically it's the secure extensions. And it allows the chip physical resources, the peripherals, the memory, the flash to be partitioned into secure and non-secure regions. wolfBoot has the ability to make available all the wolfcrypt APIs and the PKCS11 APIs in the secure domain and provide a way for those to be called from the non-secure through the non-secure callable APIs into the secure region. And that's something we're going to demonstrate today. wolfBoot also has the dual bank support, which is hardware assisted, and basically what it means is you can flip a bit in the flash configuration registers and it will remap those two banks. So on the H5, these are each 1 megabyte banks, and you can swap those. And that makes for updates, the updates go much more quickly. It also supports a key store based in the one-time programmable memory. So the H5 has a 2 kilobyte region that's split into 64 byte blocks. And it perfectly meets the requirement for a trust anchor, meaning that it must be immutable and immune to tampering. The OTP is programmed with the key store structure, which I can show you, which contains the public keys. And it's available for writing to that area is until explicitly marked as read-only. So each of the 64 byte blocks can be marked as read-only. And then we have some tools that I'll go over in a bit for provisioning the OTP memory. We also have support for post-quantum with LMS and XMSS. These are implementations that we did ourselves in wolfcrypt, so there's no external dependencies. These are both NIST certified algorithms. They can be used now in production. They're both stateful hash-based signature schemes, and they actually use hash algorithms underneath. The nice thing is the public key sizes are very small and they're very fast. The signatures are much larger though. So like ECC signatures commonly like 64 bytes. These ones are, well in excess of 1K. I'll show you that later. We also have some helpful scripts for how to tune those algorithms. We have TPM support, so we can use the TPM as a root of trust where we hash the public key and we put that into an NV. We can optionally lock it and we can assign authentication with it for pairing. And all of this can be used with parameter encryption. We support cryptographic offloading, so ECDSA or RSA verification in hardware. Measured boot like a PCR extend. We can seal a secret in the TPM based on an externally signed policy. Those policies could be PCR or other. And then we also have functionality in there to lock out the platform hierarchy by randomizing the password, which is one of the TPM requirements. So, the boot has access to the platform hierarchy, but the application after that should not. That can be disabled, but that is on by default. So now we're going to talk about how to set up wolfBoot. So we use standard makefiles, standard GCC cross compilers. All the source code is available as GPLv3 on our website or on GitHub. If you do a git clone, make sure you do the submodule init update because wolfcrypt is included in there as well. And there's also wolfTPM, wolfPKCS11 that will get cloned. All the configuration is done through a .config file that gets included from the make file. And those are basically make arguments. You can also pass them in along with the make command. We have a ton of examples for those configuration files, and we'll base our demo today on one of those. So for the STM32H5, these are some of the example configurations we use. So the architecture is ARM. It's a Cortex-M33. It's an H5. The signing algorithm here was ECC256. However, today we're going to demonstrate LMS. The hash algorithm is SHA-256. And the image header size, I'll show you later, is larger than 256. That's what it would be for ECC. So we're going to have TrustZone enabled. We're going to enable dual bank swapping. We're going to use the one-time programmable key store. We are not going to enable any of the external flash support. We will enable wolfcrypt support in the TrustZone and PKCS11 TrustZone support. Do the cryptographic, the CMSE is basically just the ARMv8 TrustZone security extensions. Yeah. This is an example for how we are partitioning the flash. So in the demo we do today, this is exactly what we're going to use, except for the swap address will not be used. This will just be F's. Doesn't apply for dual bank mode. The sector size is 8K. We've split it so that there's 256K for wolfBoot and 768K for the application. And the reason we use so much for wolfBoot is because we have all of wolfCrypt and all of wolf PKCS11 in there as well. So we're making those available to the application, and they're residing in the region of the wolfBoot. Yeah, okay. And these are some examples of some of the make options. There's actually a lot more, but the default make builds a factory.bin, which is basically the wolfBoot bin attached to a signed test image. That's the default. We have an extensive amount of documentation. You can find them all in markdown format in the docs directory. A good place to start would be compile and how to build it. The next place to start would be looking up your target specific instructions. So there's a section in here specifically for the STM32H5 and how to build it in different ways. There's a whole document just for enabling TrustZone with the STM32, another one just for the OTP setup on, well, in this case, there's instructions for the STM32. This is where the instructions are for the demo that I'm doing today. All the TPM guides for how to use all the features described post-quantum, and then how to use our key tools for signing, including using an external, like a signing service or an HSM, where you don't actually have the private key. You can just get the hash, use the external signing service, and get back the signature and pass that in. So there's instructions for how to do that. Okay, so let's get into the wolfBoot demo. So today we're going to use the Nucleo STM32H63ZI development board. We're going to showcase the post-quantum LMS, dual bank TrustZone, and the one-time programmable memory. So I'm going to go through the steps. Basically, we're going to set up the configuration. We're going to generate some LMS keys, back those up. We're going to choose one of those keys for signing. Then we're going to set up the key store in the OTP memory. So there's a couple ways to do that. We'll go through and we'll verify that's set up correctly. And then we will change some option bytes to enable TrustZone and set up this, the secure, non-secure flash regions. Then we'll do a mass erase just to clear the flash. We'll build wolfBoot in the test application. We'll flash those and then disconnect, and we should see an LED turn on, and then we'll actually get a console in the test application that boots up that we can use. So I'm going to switch over to Visual Studio Code. I've got just a latest wolfBoot that I've cloned here. And I've put the instructions for what I just showed you into this flash OTP.markdown file. The first thing I'm going to do is just do a make disk clean. You don't need to do this, but it's just a good way to delete all the executables and everything and start from scratch. So this is the configuration template that I'm copying to .config that I'm going to use. This file is set up to use post-quantum LMS on the H5 with TrustZone enabled, M33. Dual bank swapping, the partition scheme that we talked about with the swap address not being used, OTP-based key store, TrustZone enabled for wolfCrypt and PKCS11. We're going to turn on armored mode, which is a GCC inline instruction feature, which is some handwritten assembly that we made to be able to prevent somebody from glitching during a critical jump. And then we've got some middle-of-the-road settings for LMS that were set up based on some of the recommendations. You can see the signature size for LMS is over 2K, and we've reserved 8K for the header size, which is more than enough. It also happens to be a sector size, which is a good choice. I've seen cases where the vector table needs to be aligned on a sector, so it's a good value anyways. So we'll make the include target.h, which is used by the key tools, and then we would run this to generate the keys. I have already done that. I have these keys backed up. You can see that if I go here and look at my keys. I've got these 5 keys. I've already backed everything up, so instead of generating it again, I'm actually going to restore this one that I've backed up. So I'm going to restore my keystore.c file. And if you look at this, it's basically in an array of 5 public keys, and this is the key store. And each of these public keys is about 60 bytes. This partition ID allows you to assign permissions to it for partition, or you could change this to a 0 at some point in the future to revoke the keys. So with one-time programmable memory, it defaults to 1s, but you can change them to 0s. So we did that. I'm going to choose one of the keys to use for signing in this demo, and then we're going to set up the OTP key store. There's a couple ways to do this. So one way is to just to say make OTP, and it will generate an application that you can program to flash and run, and it will program the OTP. Actually, I made a slight tweak to it to make sure I don't lock my OTP, because this is a new board. I don't have very many of these boards, and I updated the instructions right here. So make OTP. And now what we can do is we can go over to the Cube programmer. We can connect to the board. This board still has the stock firmware running on it, the demo firmware. So first thing we're going to do is we're going to open the OTP primer.bin, and we are going to flash it to just the base address here. But before I flash it, I want to check the option bytes. So the board comes with TrustZone disabled. That's what I wanted to confirm. And so I'm going to go ahead and program this to the board. So this is a binary that will run, and it will program the OTP. So if you try to read the OTP right now, it's all Fs. So I'm going to disconnect. I'm going to hit the reset button on the board. Cross my fingers that it works. I'm giving it a little bit of time, but I'm going to reconnect to the board. We're going to read the OTP. Okay, so there's the wolfBoot header, and all of the public keys are programmed there. So there's 5 LMS public keys programmed into my OTP. So I'm going to disconnect from that. Well, actually, you know, there's one more thing I wanted to do if I go back to my instructions. So we did the OTP. So we did the verify, and now I want to set up the option bytes. And actually, I'm gonna do a full chip erase. Can't remember which option it is. This one. We'll do a full chip erase. It's optional, just clears everything. And then we're going to set the option bytes. So first we're going to go into user configuration. We're going to turn on B4, which enables TrustZone, and we're going to apply that. It may actually erase everything anyways when it turns on TrustZone. Then we're going to go in and change the watermark end address. So this is changing the region that I can consider secure for each bank. So this is that 256K that we talked about. And I'm also going to change this one right here. So we're going to turn that on. And it's done. So we're going to, option bytes were both programmed. I'm going to disconnect. So we'll go back here, mass erase. Okay, so now we're going to do a build of wolfBoot. So we're just going to type make. So it builds wolfBoot, all of the wolfcrypt. So again, wolfBoot is a little larger in this case because it has all of wolfcrypt in there and all of the wolf PQC 11 that's available through the so calling from the non-secure to the secure side. And now we are going to flash these. I've got the cube programmer, so I'm going to use that. So the first thing we're going to do is open wolfboot.bin. And I found that it's really this address that matters about what gets programmed. So we're going to program wolfBoot into the secure region. And then we're going to program the test app to the non-secure region at this 256K offset, 256 KB. So I'm going to open the test app. So if I go into test app and then image signed, it should be right here. Perfect. I'm going to open that, and we are going to flash this one to that address. Program. Complete. And disconnect and reboot. Okay, so now that we've programmed the device and we've disconnected the debugger, the programmer, and we have hit reset, the red LED light comes on, which looks like it's LED 3 on this board. It's a red LED. And then we have this output. So if I hit reset, I'll show you what happens. That comes up. And then we have a bunch of support for commands, like you can print out the key store, you can show a random number, and again, these are all calls from the non-secure side to the secure side. We can get a timestamp, we can do wolfCrypt test benchmarks, the PKCS 11 test. The other thing I really want to show is the ability to do the firmware update, which is really neat. So test doing an update. So what we would do is we'd sign a new version of the firmware. So let's say we sign our test app again, but with version 2. We're going to run the update command. This is going to wait for X modem. So I've never seen that. Okay, so now it's going to send the file. Right now, the orange LED is blinking slowly, maybe twice a second, and then the green LED is flickering because that's the one that's doing the UART traffic. At the end of the transfer, the new image will be in the update partition. So right now, the new firmware, and it actually says end of transfer, new firmware version, and it's read it back as 2. It's triggered the update, and so now we just need to reboot the board. I think I can just hit reboot. Let's see what happens. And so it did the swap, and now we're running version 2. And if I hit the reset button, we're still running version 2, which I think is fine, because I'm not. I think it marks success, but there is a success command. I'm not clear on that. But that's the full demo, and anybody's welcome to try this out. You can run the benchmark, you can run the wolfCrypt tests, and those are all being done through the non-securable functions inside wolfBoot there. These slides can be made available by request. I tried to include all the details for how to go through these same steps in the slides. And now we're going to do a live Q&A session.
Thank you, David and Mina. We'll move on to the Q&A session. So I have a question. Does wolfBoot support STM32H5 Cortex-M7 processor?
Yes, it fully supports the H7 and all the variants of it out of the box. And you can find all the information on that in that targets markdown file.
They have another question. Does STM32 board have persistent secure storage for private keys that is not erased when power is off?
Well, the OTP is a good place for that. I did notice in the reference manual for this chip, when I'm looking at the security features, that there's some software, or there's some memory regions that you can put some symmetric keys, but those don't persist reset, and those can be used by the cryptographic hardware. In my opinion, the OTP is the right place for the keys, especially root of trust type keys.
Okay. We have another question. Are the DPA and glitch countermeasures implemented in hardware or software?
It's software. So we have some handwritten inline assembly, GCC syntax and inline assembly specifically for Cortex-M that, when we get to the point where we do a critical jump, so let's say we've checked the integrity of the firmware, we've checked, that the signature is correct, and we say, if those are all true, then jump to the application. We had cases on some hardware where people could glitch the power rail and skip that critical jump. So we implemented this armored mode that lets you, it does a bunch of assurances to ensure that expression is actually checked correctly. The DPA side channel stuff, a lot of that has to do with the chip manufacturer. In this case, this chip has those. So if you tried to look at power consumption during some of these, cryptographic operations, you aren't going to be leaking anything. The other part is this is all public operations during a boot process, so there's no private keys involved. And then all of the cryptography that we use in wolfCrypt is timing resistant. So even if there was private key operations being done, there's not anything timing-wise that's leaked. So.
Okay. So I have another question. How is wolfBoot different from the bootloader available from ST, OEM, IROT, and URT?
Yeah, so ST has an ST IROT and an OEM IROT option. The ST IROT is only on the H573, and it's a secure boot mechanism, a whole infrastructure that they've developed, which I think they probably have a whole separate documentation for, and I don't have experience with yet. We do have the intention to eventually implement ourselves as an OEM IROT option. And there is a representative from ST on who might be able to shed some light on that question as well. That would be Pasu. I don't know if he has any thoughts.
Yeah, I'm not entirely sure on that either, Dave.
Okay.
Okay, so there's another question. Will you be supporting dilithium for PQC signing?
I'm not sure on that. I think Anthony, he's on here, he's our post-quantum expert. He's probably best to answer that question.
Yeah, so this is Anthony. How are you all doing? That's a great question in the sense that there's no reason not to put dilithium, to support dilithium within wolfBoot. We have our own dilithium implementation. So it's got larger keys, so that's one reason why you might not want to, but it is a good general purpose signature scheme. So you got to look at the motivation for why we did XMSS as well as LMS. The motivation was that there was this CNSA 2.0 document that came out that said, hey, the first thing we want to see are software signing tools migrated over to post-quantum. And they specifically pointed out that XMSS and LMS were fit and usable today, and we should get moving on them now. So that's what we did. That's where the motivation came from. But if you look now at dilithium, where's the motivation, right? So if a customer came to us and said, we really want you to use dilithium, then yeah, for sure, we would get dilithium right into wolfBoot right away. I hope that answers your question.
Okay. There's another question. Is a wolfBoot a replacement or common adjunction to STM TrustZone software?
I believe it's a replacement, but Daniela, do you have any knowledge of that? Because I feel like what we've done in the TrustZone is like a full replacement of what's there.
Yeah, I think that this take is correct in the sense that wolfBoot in this case has the dual function of being the secure bootloader, but also the TrustZone manager, so it doesn't require any external components to do so, and it manages the secure areas in a way that a non-secure application can call into non-secure callables that are directly managed by wolfBoot. So in this case, the TE manager from ST is out of the picture.
Thanks.
There's another question. What is the sequence boot of the electronic board?
Well, there's boot ROM on the chip, and out of reset, it looks at the vector table and it jumps into wolfBoot. We start up peripherals, we set up TrustZone, we do all the verifications, and then we jump to the application. We do relocate the vector table and jump to the application. I may be simplifying it, but yeah, I mean, that's the gist of it.
Okay. Is wolfBoot PSA certified?
We haven't done PSA certification yet on it. We could. We haven't been asked to do it yet. And, we typically probably wouldn't do that unless a customer wanted it.
Okay. We are also considering another security solution from Seagull. What are the benefits of using wolfBoot over Seagull?
I'm not aware of their boot solution. Daniela, have you seen it? Do you know anything about it?
So can you repeat the question, Shizuka, please?
So it's Segger, SEGGER. Apparently they have their own secure boot solution.
Okay.
Yeah, I don't know anything about it, so
yeah, not enough.
They're not open source, so it's difficult for us to compare something like that.
Okay. Is there a replay protected memory block in any of STM32H5 development boards?
Not sure what that is. That could be that region of memory, key memory I was talking about, but I haven't heard that term used.
That may be referring to RDP or
maybe, yeah. So the readout protection, there's levels you can set that basically lock down configurations of the option bits and JTAG and all sorts of things. But yeah, if you look at the reference manual, under the security features for this, so chapter 3 and specifically 3.1, there's a ton of details on this.
The person say RPMB.
Yeah, I don't know anything about that. Sorry.
Perfect. And there's another question. What transports are supported for transfer of firmware images? Can firmware images be sent over a network stack?
So we leave it up to the application, right? So if your application has connectivity of any sort, it could be your, it could be a socket, network socket, it could be a CAN bus, doesn't really matter. We're transport agnostic. So in your application, you transport the firmware and you put it into your update partition and you signal wolfBoot that you have an update ready and you reboot. And wolfBoot handles that after reboot. So we support any transport. In our demo, we used UART with Xmodem.
Okay. I have another question. Do you have any support for RISC-V SoC, for example, microchip PolarFire or any ARM-based FPGA SoCs?
Yeah, system on chip. So yes, we do. We implemented some of the 32-bit RISC-V support in it's a Hi5, one of the early revs of the Hi5. We do have plans to eventually implement PolarFire support. We do have the hardware, and we will continue to expand our RISC-V support. Danielle, anything you want to add on that? I can't think of anything.
I think you described that perfectly. We do support many architectures. Of course, wolfBoot is not just ARM, it's not just Cortex-M for sure. And it goes from Cortex-A, but also RISC-V, 32-bit, and up to even x86 64 targets as a BIOS replacement. So we support PowerPC. We have a very long list of architectures supported there.
There's another question. Is it possible to implement just the same approach with BU585i IoT02A board?
I believe so. I believe the U5 has the same TrustZone. I believe it has the same OTP. I think you could do the same demo on that board.
That is correct, David. Yeah.
Perfect.
And I'm pretty sure we support it out of the box already. You could do it.
Perfect. What happens if application to boot is larger than the 768 kilobyte left in the internal flash? Can wolfBoot authenticate and locate it in external QSPI or XIP QSPI?
Yeah, so the update partition can be external flash. That's correct. So you could have a much larger application if you had external quad SPI flash, for example. If the hardware supports quad SPI with execute in place, yeah, we've done that, and that can work fine too with a little configuration change.
Okay. Another question, are these products eVita Medium certified? Are these products free to use? What is the difference of wolfBoot and the secure boot products that the SD natively offer for their hardware crypto microprocessors such as STM32H5 S3L?
I don't know the answer to that. I haven't heard of eVita Medium certified. Has anyone else?
But I think part of the question was a little bit the comparison with the SPSFU, which you left in your slide deck probably.
Yeah, I skipped those due to time reasons, but they are in. I do have some slides. There's 2 slides in there, and I compare the SPSFU with wolfBoot, and there's a bunch of differences for sure. In fact, even on the H5 the SPSFU is not supported yet. So,
there's another question. What is the wolfBoot pricing?
I'm an engineer. I don't usually answer that question, but the best thing to do would be to send an email to LicensingNet. We have a standard pricing model, and usually it's royalty-free perpetual license.
Yeah. Another question, how long does it take to get through the bootloader and into the user app at each boot up?
Yeah, I didn't measure it on this target, but from the time I hit reset to the red light coming on, it's a few hundred milliseconds, maybe 200 milliseconds. We have done benchmarking on different algorithms, and we've posted those. I can't recall off the top of my head where those are, but you can always send an email to fax if you'd like to get a copy of that.
Yeah, it's usually even less than that, David. It's between a few tens of milliseconds rather than hundreds, especially for lightweight algorithms.
There's another question. So if wolfBoot replaced Trusty, which is PSA certified, would it be required to be at the same level of compliance?
Can I take this one, David?
Yeah, please.
Thank you. So let's say that PSA compliance comes from the fact that ARM has tried to standardize their own way of accessing crypto calls through what they call PSA interface, which is not an actual ratified standard. So there are several ways to do this. There are a few ones that have been already a standard and established standards just even outside of the ARM world, let's say, for a long time. And one of this is PKCS11, which has been extensively used, for instance, on smart card applications for decades now, and it's well established and an actual recognized standard. So that's the reason why we chose to go with PKCS11, because it's let's say more universally supported. In fact, I think about operating system like FreeRTOS that need a translation layer between PKCS11 calls in order to access PSA engines. So that's been, let's say, a precise choice from our side to extend as much as possible the support. Said so, wolfSSL already has a PSA plug from the TLS point of view, and we could extend our engine option for wolfcrypt on the other side to support PSA, let's say, relatively quickly. It's not a big engineering effort. The concept is in fact the same. We're talking about translating between APIs here, so that wouldn't be a problem. But so far we didn't have this kind of request from our users or customers.
There's another question. XMSS LC hash-based signature key can be hard to manage in a production environment. They have to be created and using HSMs, and backup failover options are limited. Do you have any recommendation for handling that?
This is Anthony again. So we also in wolfSSL also do keygen and signing operations within a library. You are correct. This is a pitfall of these algorithms, and notably, wolfBoot as a product only does verification of these signatures. So when it comes to keygen and signing, if you follow the guidance of NIST and other standards organizations, yeah, it has to be done in an HSM. And so I would say that you would probably follow that guidance. That said, maybe that's a good reason. This might tie into the previous question about dilithium. That might be a good reason to move to dilithium later on.
So from the wolfBoot point of view, as David has already mentioned in his presentation earlier, we do support a mechanism that includes an HSM in the loop, which means that basically we do all the operations to create a header. We hash the firmware and allow a third-party HSM to sign the actual hashed payload, and then include as a third step the signature to the final manifest header. And this is described in our documentation as the three-step signing, including an HSM in the loop, and it's in signing.md in the docs directory. And we have demonstrated this with a few partners that have that offer this support as a HSM, and we recently also added it's not just related to PQC, of course, that can also be done with the pre-quantum cryptography, and we recently added documentation to enable, for instance, the second step, so the signing step in Azure cloud services using the Azure key manager.
So there's another question: how to prevent the firmware from reading the OTP?
Yeah, so I think the current design, all the contents of the OTP are public. And I don't know if the H5 chip has a way to prevent the OTP specifically from being read from the application side, but there is ways to configure the option bytes to actually make unavailable the boot region. So if somebody tried to read the addresses of where the wolfBoot or the secure side is, that would actually crash or cause a fault. You'd have to look in the reference manual for the H5 specifically if there's a way to do it for the OTP. I don't know the answer, but the content in there is fully public. In fact, that could be an advantage because you have those roots of trust and you can use them from your application side as well.
Okay. What does the manufacturing flow look like? Does wolfSSL provide HSM for production manufacturing to provision the devices?
We don't provide an HSM. You'd have to use a vendor for that. Daniela, what are your thoughts on the manufacturing process?
Well, we are very flexible on the provisioning and deploy scheme. That's why also we have options to include HSM in the loop, and of course the way you provisioning your keys might depend on your manufacturing process itself. So we rather tend to adapt our solution to your process than enforcing a specific procedure for that. So in the case of the demo shown today, for instance, it would be best to separate the provisioning of the OTP from the actual installation of the bootloader itself. But once those two are in place, basically only signed and authorized applications can be run on the device. So that basically depends on your final devices provisioning and manufacturing design, let's say.
Does wolfBoot support its own decryption mechanism for encrypted firmware updates for chips that do not have on-the-fly decryption?
Yes, we support the ability to have encrypted partitions externally, or send, when you sign them, you can also encrypt them and send them down. On internal flash, currently, we only support having them unencrypted. I believe there's some talk of a future request that could allow on-the-fly decryption in certain environments that have enough resources. Does that sound right, Daniela?
Yeah. The obstacle there is the execution in place, because of course if the firmware needs to be executed in place, so in the case like we shown today, straight out of the internal flash, in that case there is not much we can do about it. But if you have enough RAM, for instance, in your target to load the firmware to be authenticated and boot and the stage there, then of course we do have the possibility to decrypt while loading to RAM, and that's something we do, for instance, on non-embedded target very often. But otherwise, by default, the encryption on microcontrollers is mostly dedicated to protect attacks like wiretapping the SPI or intercepting SPI reads by physically connecting to the SPI wires, let's say. So everything that's stored in an external flash can be enforced to be encrypted, and that's also, of course, has a counterpart in the signing tools, as David was mentioning, that can encrypt end-to-end when you're signing the firmware, so that it's transferred encrypted, and then You just need, of course, a way to decrypt it on the device, and that covers all the use cases except the executing place.
Okay. There's another question. Can SD micro factory provision chips with images signed by wolfSSL is a minimum order quantity?
I'm not sure. Pasu, do you have any
So
guidance
we do,
for factory?
yeah, we do have factory provisioning available. I would have to check what the minimum order quantity is, but I'm also not sure how we partner with our vendors for this. So I'd have to go back and check on that. Not really sure exactly.
Okay. Okay, perfect. Thank you guys for the insightful question. And thank you, David, Anthony, Daniela, Pasu, and Mina for hosting an informative webinar. And please don't forget to follow us on X at wolfSSL and at st_world, as well as our LinkedIn and YouTube channel. If you have any further question, please email us at fax@wolfSSL.com. And thank you again, and see you next week for getting started with the call. Thank you.